So this is a continuation of my discussion on the periodic table. Valence electrons. So valence electrons are the electrons in the outermost energy levels. You might recall from Bohr's model, it was electrons in the last ring. For this is really no different. It's electrons the highest value of n, meaning principal quantum number. So for example, lithium is 2s1, has 2 valence electrons. Beryllium is 2s2, 2 valence electrons. Boron 2s2, 2p1, that's a total of 3 valence electrons. So basically we look up the number in front, add up the superscripts, that's the number of valence electrons. Electrons below that are called the core electrons. So for example, beryllium has electron configuration of 1s2, 2s2. We have 2 electrons in the core, and I have 2 electrons that are valence. Okay. This chart shows basically the same thing. Also shows basically the valence electrons. Now when it comes to the d electrons here, for example, scandium says 4s2, 3d1. It turns out the d block, the electrons within the d block can be accessed and thought of as valence electrons. So scandium Sc has basically a configuration of argon core, 4s2, 3d1. So when it comes to elements in the middle here, the middle part of the periodic table, these d electrons will also count as valence. So scandium actually has 3 valence electrons, and that's going to have a big effect on electron configurations for these elements, because the elements in here do not always follow the pattern. Alright, so they're going to be some exceptions to the rules. I'm going to go going over that. Also on this periodic table here, notice what they did. They took L, A, and AC, they put them in the D block where they belong, left the space here, and then put the F block where it belongs. So unlike the table I showed you in a prior video, I made a point of this, is that some tables put L, A, and AC at the bottom. This table here put them where they properly belong. Okay, so it shows all the different elements and based on and their valence electrons. I'm not going to worry about valence electrons in the F block, but you should be able to understand that within the D block there's going to be some exceptions to the rules. Okay, these are some examples here. These are similar to the ones I already did in the prior videos. I'll leave them for you. If you have any questions about these, let me know. This is the diagram we did earlier, and again in the prior video, showing how to put the electrons in from low to high. This goes up through the up to the 4D. So you should be familiar with this filling pattern. This pattern matches the periodic table. Alright, so why do we get, for example, multiple p orbitals? Why do we get multiple d orbitals, etc.? What's going on here? Why are the 3d electrons, between the 4s and the 4p? Why are these orbitals here where they are? So there's some reasons behind this. First of all, the sublevels in each principal energy cell of hydrogen all have the same energy of other single electron systems. We call orbitals with the same energies being degenerate. For multi-electron atoms, the energies of sublevels are split, which is caused by charge interaction, shielding, and penetration. So based upon how the electrons interact with one another, that's going to cause the energies to not necessarily follow, for example, a predicted pattern. The lower the value for L, the less energy or the sublevel has. So generally speaking, so S is lower energy than a P, P is less energetic than a D, D is less energetic than F. However, due to some of these interactions, these effects, interactions, shieldings, and penetration, that can cause these orders to be flipped around a little bit. Coulomb's law basically says the potential energy is the positive for like charges. Basically, we have repulsion or attractive forces. Q1 and Q2 are charges. R is a distance. Okay. So the potential energy is positive and decreases as the particles get farther apart as r increases. So basically the force of attraction gets smaller as the value of r increases. So if you put two particles farther apart, they feel each other less strongly. So the force of attraction can go down. For opposite charges, they get attracted. The point is, the strength of the interaction depends upon the magnitude of the charges and then the distance. That's all that really matters, ultimately. So electrons are more strongly attracted to the nucleus of the positive 2 charge than the nucleus of positive 1 charge. Remember, electrons have negative charge, protons have positive charge. So electrons closer to the nucleus are going to feel the nucleus more strongly. That's what all that really says. We have something called shielding and affect the nuclear charge. So here's a situation where I have 3 protons in the nucleus. I got 3 electrons around the atom. The electron farthest away out here is being shielded by the 2 electrons on the inside. These electrons are interacting or interfering with the attractive force between the nucleus and the electron. That's being broken up. That's called shielding. So basically this last electron is not going to feel the nucleus as strongly, just because this negative charge is in the way. Penetration basically deals with how close the electron is to the nucleus. This one right here is the closest to the inside. Therefore, it feels the strength of the nucleus as strongly, much stronger. It's these types of interactions which can affect how the orbital splitting, how the orbital fill patterns, and so on come about. So basically, the effect of all of this, we have the 1s orbital, we have a 2s orbital, and also the 2p orbital. And we can see here from this diagram, so this is distance on the x-axis and total radial probability in the y. It's basically just electron density, how close it is to the nucleus. What we find is that the 2s orbital penetrates a little bit into the 2p inside, closer to the, between the 1s and the 2p. So the 2s orbital penetrates more deeply into the 1s orbital than does the 2p. The weaker penetration of the 2p sublevel means that the electrons in the 2p sublevel experience more repulsive force. They are more shielded from the attractive force of the nucleus. The deeper penetration of the 2s electrons means electrons in the 2s or sublevel experience a greater attractive force to the nucleus and are not shielded as effectively. So they don't get interfered as much. The penetration causes the energies of sublevels in the same principal energy level not to be degenerate, meaning the same energy. In the 4th and 5th principal levels, the effects of penetration become so important that the S sublevel lies lower in energy than the Ds. So this is why the 3Ds come before the 4. The 3D comes before the 4. The 4S comes before the 3D. Okay, it all comes to these effects. So the point of all this is that, due to the way the orbitals interact with one another, the ordering can therefore vary among elements, causing variations in electron configurations of the transition metals and their ions. So basically the rules are not black and white. It all has to do with the way the electrons interact with one another. That's kind of the moral of the story here. So we know that because of the sublevel splitting, the 4s sublevel is lower in energy than the 3d sublevel. Therefore, the 4s fills before the 3d. So, there we go. You have to memorize that. Although the difference is not large, because of this, we can sort of treat these 3d electrons as being like valence electrons, meaning they can be used for making bonds. And it leads to also end up with irregular configurations. Alright, so this is what I'm saying. You need to know this. Alright, so you need to know this list. For example, chromium is expected to be, if you follow the rules, 4s2 3d4. Let me find my periodic table. Go back and I'll repaste this down here. clean this up a little bit. Get rid of this and get rid of this stuff. So chromium is right here. We expect chromium to be argon core. Chromium should be argon core 4s2 3d4. 4s2 3d4. What's happening here is that one of these s electrons, so we have, this is the 4s, 1, 2, 3, 4, 5. We have the 5 of the d orbitals, 1, 2, 3, 4. That's what we expect. What's happening is that one of these electrons here is moving there. We end up with 4s1 3d5. So you need to know that. Okay. Basically, what's happening now, we end up getting a halfway field 4s, a halfway field 3d. Having halfway filled is more stable. Why is that the case? Well, what is the charge of an electron? Electrons are negative and they want to repel each other. So we're taking the electron out of here and moving it over here. I'm now separating electrons farther apart in space and maximizing their, basically I'm making the energy smaller. Okay, I'm minimizing the electron-electron repulsion by separating them farther in space. Copper, same thing, same idea. 4s2 3d9. I'll mark copper here. Copper is right here. Copper ends in 4s2 3d9. So I'll draw copper. I can take electron away from the 4s and move it over to the 3d. I can fill that up. That ends up being overall lower in energy. All this ends up being energy related. Molybdenum, 5s1 4d5. Notice molybdenum is in the same column as chromium. Well, once you know it. Silver is the same column as copper. So is gold. Okay. So basically we can see now ruthenium, I don't expect you to know this one. I'm gonna cross this off the list. You don't have to know that. Okay. And palladium, I'm gonna cross that off as well too. You don't need to know that one either. These three you should know. It turns out that chromium, molybdenum, and then we have copper, silver, gold. These are all going to follow the pattern I showed you here. Okay. So make sure you at least know this, and make sure you understand as well chromium, molybdenum, copper, silver, gold. Make sure you know those 5. They're not going to follow the rules. The F block is even more crazy. These are going to do more strange things. You don't need to know any of that either. But make sure you memorize these. Again, electrons are trying to get as low of energy state as possible, and they can do this by changing orbitals.